Good morning, fellow mathematicians. Welcome back. In today's video we are going to tackle the Fresnel integrals, finally. The Fresnel integrals are two integrals from physics, and they consist of two improper integrals from minus infinity to infinity of the cosine or sine of x squared times dx. Okay, so that looks interesting, and trust me, it took me ages to solve them with the way I'm going to show you today. And most of the steps are kind of counterintuitive, and they were fucking hard. They were hard as hell. And we are not going to use complex analysis. We are going to use the Leibniz rule for integration. And if you don't know what it is, just take a look in the description. There will be a link to the corresponding video right there. Okay, let's go ahead and get started. A wise mathematician once said, "Let's kill two integrals with one stone." I don't know if someone ever said that, but still, we are going to do this today because you can solve both integrals by solving just one integral. And we are going to solve this integral, the improper one, from minus infinity to infinity of e to the minus I x squared times dx. Why do we solve both of them using this one? Because we can split this up in a real and an imaginary part. So the real part is this one and the imaginary part is this one. So I guess you know how complex numbers work. So we can do this. We are going to use the Leibniz rule. So that means we have to introduce a parameter or something like this. Okay, we are going to introduce something completely new. We are going to say that some integral, I in terms of t, is defined as follows. So that's just the integral from 0 to t of e to the minus I x squared times dx, but the whole thing squared. Okay, so how can we represent this integral with this one? If you take a closer look, you might see that this is an even integrand. So what we can do, we can rewrite this as follows. So this integral is nothing else than 2 times the integral from 0 to infinity of e to the minus I x squared times dx. And now you might see what I'm talking about. Let's call this guy just I. Okay, so how can we write I in terms of it? Okay, so let's conclude. You might see that I equals to 2 times the square root of I in terms of t equals to infinity. Okay, I hope you guys see why this is true. Okay, and all we want to do now is calculate this integral right here. And when using the Leibniz rule for integration, you might want to differentiate an integral. So we are going to start off with this step. Okay, so let's differentiate I in terms of t over t. So what do we end up with? So that's dt of the integral from 0 to t of e to the minus I x squared times dx, but squared. And now we have to use the chain rule, like Dr. Payam would say. We are going to use the chain rule. Okay, so at first we have to take the outer derivative. So the outer one is quite simple. It's just 2 times the integral from 0 to t of e to the minus I x squared times dx. Okay, and now we have to take the inner derivative. And now you should remember how the Leibniz rule is constructed. So the first part was just the integral times the partial derivative of the integrand. So the partial derivative in terms of t times e to the minus I x squared times dx. Okay, the next step, we evaluated a constant at the upper bound. So this is plus e to the minus it squared times the derivative of the upper bound in terms of t, because we are differentiating in terms of t. Okay, and the last step, we subtracted a constant evaluated at the lower bound. So that's e to the minus I times 0 squared times d of 0 over t. Okay, can we conclude something? Okay, this vanishes because e to the minus ix squared is just a constant when you differentiate it in terms of t. So this vanishes, becomes 0. This is just 1 because d over dt equals 1, so we end up with e to the minus it squared. Okay, so that becomes 1. And the last thing, well, we are differentiating a constant, so this becomes 0 too. So this equals to 0. So what do we end up with finally? So we end up with 2 times the integral from 0 to t of e to the minus ix squared times dx times e to the minus it squared. Okay, and the integral is a linear thing, so we can bring this little constant in. So finally we end up with 2 times the integral from 0 to t of e to the minus I, and I'm factoring out the minus I, x squared plus t squared times dx. And we are done with the first step. And we are going to call this one I prime of t. Okay, because we differentiated I of t. Okay, and now we are going to move on with a little substitution. So to show you where this substitution comes from, I'm going to play around a bit with the exponent right here. Okay, so this integral is equal to the integral, 2 times the integral from 0 to t of e to the minus I t squared. So I'm going to factor out t squared. So what we end up with is just 1 plus x over t, but this squared. I hope you can see where this comes from. Okay, and now we are going to introduce a new substitution, and we are going to call the substitution u, for example. So let some u equal to x over t. And that would mean that du equals to 1 over t times dx, and this is equivalent to t times du equals to dx. Okay, so far so good. What can we do next? We are going to plug all of this stuff in. So I prime of t equals to 2 times the integral of. Okay, now we have to plug in the lower limit. So if we plug in 0 into this x, then u equals just 0. So that's cool. And if we plug in t into the x, that's t over t, so u equals to 1. That's nice. So what else do we have? So we've got e to the minus it squared times 1 plus u squared times t du. Okay, that sounds great. And yeah, we can bring this to the front if you like. But we need those 2 terms in the next step. So keep in mind that there's a connection to this one. Or whatsoever. Okay. The next thing is really counterintuitive, and you should just try following my thought process here. Because we are going to see what this whole term equals to. So we are working with I prime of t at the moment, but we want to go back to our original I of t somehow, so that we can plug it into this equation. But if we want to integrate this, it's kind of problematic. So we have to think about a way to get rid of the integration somehow. You will see in a minute what I'm talking about. So we are going to integrate later in terms of t. So maybe we could try to isolate some kind of differential in terms of t, so that the integral and the differential cancels out. It's kind of hard to explain. I'm just going to show you what I'm talking about. Sorry. Okay, so let's observe something. So we are going to observe the following, that 2 times t times e to the minus it squared times 1 plus u squared equals to something. So we can make this equal to the partial derivative in terms of t of, okay, so that's equal to e to the minus it squared times 1 plus u squared over minus I 1 plus u squared. And I hope you can see where this comes from. So if we differentiate this in terms of t, the minus I and 1 plus u squared gets dragged down. So this cancels out because we don't have this on this side, so we want this to cancel out. And also we have to take the derivative of t squared, so that's 2t, and we end up with this 2t. So that's great, and we can write this a little bit different. We can expand this fraction, with I over I. So this becomes the partial derivative in terms of t of I times e to the minus it squared times 1 plus u squared over 1 plus u squared. And we can plug all of this in here and see what we get. So this is equal to that I prime of t equals to the integral from 0 to 1 of the partial derivative of t times I e to the minus I t squared 1 plus u squared over 1 plus u squared times du. And here's one crucial observation. Here's a partial derivative in there, so we can reverse the Leibniz rule. Why can we do this? We can reverse the Leibniz rule. That means we can interchange those two, the integral sign and the differential, because our upper and lower limit aren't in terms of t right now. So we can do this. That's the special case of the Leibniz rule. So this equals to d over dt times the integral from 0 to 1 of I e to the minus I t squared 1 plus u squared over 1 plus u squared du. And that's great. That's exactly what I was talking about, because if we integrate this I prime of t now in terms of t, that would mean that the integral and this one kind of cancel out. So if you take a derivative inside the integral and then you integrate it again, you just end up with the original function inside the integral. Okay, so let's see what we get. Let's integrate this.
Dr. Pam.
I didn't say that. Okay, let's integrate this one. So what happens if we integrate I prime of t? That means we end up with I of t. Okay, so that means we have to integrate the right side. So that's the integral from d over dt of this whole chunk. So 0 to 1, I times e to the minus it squared, 1 plus u squared over 1 plus u squared times du, and I'm going to put parentheses right here, times dt. And I hope you can see what I was talking about. So this kind of cancels out if you say it kind of not mathematically correct. So what we end up with is just the integral from 0 to 1 of I times e to the minus it squared 1 plus u squared over 1 plus u squared times du plus some arbitrary constant c. Okay, because we are dealing with an indefinite integral right here. So don't forget this one. That's really important because we have to find out this constant now. Otherwise the whole Leibniz rule wouldn't make any sense. Okay, so now we have to find c. How can we find c? Well, I hope you guys still remember what our original I of t equals to. So that's just the integral from 0 to t of e to the minus ix squared times dx, but squared. So this is completely equal. What can we do? Maybe we should try to get 0 on one side so that we can isolate our c. Okay, how could we get 0 somewhere? Maybe we could say that I of t equals to 0. The t equals to 0, not the whole integral. So that would mean that the right side is just the integral from 0 to 0. So this vanishes completely, it's just 0. So let's conclude what we just find out. So I of t equals to 0 equals to, okay, so that's the integral from 0 to 0 of e to the minus ix squared dx, the whole thing squared, and this equals to 0. But this is still equal to the integral from 0 to 1 of I times e to the minus I. And now we are plugging in 0 into here because it's in terms of t. So times 0 squared times I plus u squared over 1 plus u squared times du plus c. So now let's conclude what we end up with. So this is equivalent to 0 equals to the integral from 0 to 1 of. So this just becomes 1 because it's e to the minus 0. So this is 1. So we've got I over 1 plus u squared du plus c. And now we can bring this term to the other side so that we can isolate c. So that's equivalent to c equals to minus I times the integral from 0 to 1 of du over 1 plus u squared. And this is just the arctangent of u. So that's minus I times the arctangent of u from 0 to 1. Okay, that's great. And now we can find out what the arctangent of 1 and what the arctangent of 0 is. So I'm sorry, this is kind of messy. I don't have enough space. So c equals to I minus I, I'm sorry, times the arctangent of 1 minus the arctangent of 0. So you can plug this into your calculator, or you can find it out by calculating it by hand. But the arctangent of 0 is just 0, and the arctangent of 1 is pi over 4. So c equals to minus I times pi over 4. And that's great that we find this out, because we can plug this into our first relationship that we find out between I and I of t. So let's plug this in. Okay, nearly done, so bring this to an end. Okay, so we know that I equals to 2 times the square root of I of t equals to infinity. Okay, and now we can plug all of this in. So this is 2 times the square root of the integral from 0 to 1 of I times e to the minus I, and the limit as t approaches infinity, I'm going to write it right here. Okay, of t squared times 1 plus u squared over 1 plus u squared times du, that's a real mess, minus I times pi over 4. Okay, so I hope you guys know what this integrand equals to, because if we plug in infinity right here, that's e to the minus infinity, so that's 1 over infinity, that's 0. That's great, so this one vanishes. And what we end up with is just 2 times the square root of minus I times pi over 4. And we can simplify this a bit. We can split this up because it's multiplicative. So this is 2 times the square root of pi over 2 times the square root of minus I. Okay, so this cancels out, that's great. So that's the square root of pi times the square root of minus I. And I'm going to make another video on this one, but I hope you trust me, because the square root of minus I just equals to the square root of pi times, okay, so that's square root of 2 over 2 minus I times the square root of 2 over 2. And yeah, we can distribute the square root of pi and bring it into those roots. So finally, our integral is equal to the square root of 2 pi over 2 minus I times the square root of 2 pi over 2. And I hope you still remember what I was talking about in the beginning, because I equals to some special complex number. So this is just the integral from minus infinity to infinity of the cosine of x squared times dx minus I times the integral from minus infinity, sorry, to infinity of sine of x squared times dx. Okay, and here's the last little observation. So this is the real part, and this is the real part. So this integral equals to the square root of 2 pi over 2, and this is the imaginary part, and this is the imaginary part. So this whole integral right here equals to the square root of 2 pi over 2. And here's the coolest thing about it. Those two are completely equal. So it doesn't matter which one you calculate, they are completely equal. And that's extremely cool. And yeah, those were the Fresnel integrals, and that one was a hard one. It took me so long to figure it out, because it's just pure luck. With the Leibniz rule, you are trying around and you're trying and sometimes you just don't get to any conclusion at all. But this one worked out pretty well, and I hope you enjoyed this video. This was a real monster. It's completely insane, but I really love it. It's so much cooler than using complex analysis, at least in my opinion. Still, I hope you liked this video. It took me quite some time to film this video because I failed miserably, because I suck at filming videos and speaking English. So I'm glad that I finally was able to release this video. And yeah, thank you for watching. Today's better weather out there. Thank you for watching. See you in the next video, and leave a like, subscribe, and if you want to recommend me, feel free to do so. See you in the next video. Goodbye. Colombia.